Hello, today we will continue working with chemical reactions and equations, and once again we will be dealing with translating verbal equations into chemical equations. Chemical equations are represented by symbols, chemical formulas, and of course, as a chemical equation, the equation must be balanced in terms of the number of atoms on each side. Alright, here are some examples for analysis. The first example is the reaction between zinc and oxygen, which leads to the formation of zinc oxide. Okay, let us depict this chemical reaction using symbols of the respective elements involved. Zinc undergoes a reaction with oxygen. I sincerely hope that you are well aware that oxygen, being a simple substance, is represented by the chemical formula O2. No other way to describe it. This is going to be a mess. First, on the right side, we write zinc, and second, we write oxygen. We can check this formula whether it is correct or not using the charge of oxidation state. Zinc has an oxidation state of +2, while oxygen has a -2. So here's the deal. The formula will be like this, but if asked to place the charges on the left side, I'll remind you that for zinc and oxygen, for simple substances, the oxidation state is 0. Alright, we gotta even the score. Well, let's remind ourselves that first and foremost, we start with the element whose index is greater, that's oxygen. On the left side, he has 2, on the right side, 1. Oxygen is divisible by 2. We divide 2 by 2. Don't write units. We divide 2 by 1. So it turns out that we have 2. We put it in front of zinc, and we need to equalize zinc. Zinc comes second. We have 1 on the left and 2 on the right, which is a multiple of zinc, also 2. We divide 2 by 1 and get 2, and we divide 2 by 1, the 2 remains. This is a reaction of a compound. Besides the fact that she's working with oxygen, we could also add that it's an oxidation reaction. It can happen as a burn, so like zinc can burn in the presence of oxygen. Yes, you need to heat it up well for that. Additionally, I want to emphasize that during the equalizing process, I stress the significance of the element's symbols and their order once again. However, this particular note is absolutely necessary if you are not very skilled or proficient at it. So, in my view, this is the way the order should be written. However, if these equations are not a problem for you anymore, and you can handle them easily, then underlining is not required. And keeping track of the least common multiple is also necessary if you're getting confused and not quite understanding or accurately interpreting those interactions. Well, I guess that's something we'll have to do then. Now, the second reaction is more complicated. This is the decomposition process of copper nitrate, which has a valence of 2. Copper nitrate is a compound that is classified as a salt. At the same time, since copper has a valence of 2, I can use valence in this case. For example, in this case, copper has a valence of 2, and the valence of the acidic residue H3 is 1. If we go through the valence stage, according to the Cresta-Kuprum rule, H3 twice. This is a breakdown reaction, and I'll add that this reaction only occurs at a certain temperature. Copper nitrate won't decompose on its own. So what does he end up with? We're being told that it turns out that copper O and the valence of copper is maintained, and as we know, the valence of oxygen is also 2. So there are no additional indexes. The second product of the reaction is nitric oxide, nitrogen dioxide. Dioxide, that means the formula is NO2. If asked to assign valence in this formula, we would say oxygen has a valence of 2 and nitrogen has a valence of 4. However, this is a name that has global recognition. Additionally, the oxygen is the third product of the chemical reaction. As we can observe, this interaction is significantly more complex, and as a result, achieving equality will be a challenging process. So, which element are we commencing with? Look, in this regard, we can commence with oxygen. His index is the highest. He has obtained 6 on the left side. However, oxygen on the right side, let us observe. If here it is in one substance, then on the right side it is present in all 3 substances. That's why the least amount of time you can't work here. Well, then watch what we're going to do. We will count the oxygen on the left side 6, and on the right side of it is 1 in addition to 2 and another 2 subtracting 5. That is an unusual number, and it is peculiar specifically in the substance copper. And then we'll put a coefficient of 2 in front of cuprumo so that the oxygen content here becomes even from an odd number. Let's begin from the beginning with this pair. So we have copper on our left side. Let's now equate it with copper as the second stage. Here she is alone. On the right side there are 2. So before the cuprumantrid Vajnoy formula, you need to put a coefficient of 2. Copper is equivalent. Currently we have 2 times 2, which equals 4 nitrogen on the left side, and on the right side it is 1. Then let's place a coefficient of 4 on the second shift. The next step in the process is to check the levels of oxygen. On the left we have 3 oxygen to 2, 6 to 2, 12, and we still need to check on the right. There are 2 oxygen atoms here, plus another 4 times 2, which is 8, and plus 2, which is 12. In this case, since the decomposition reaction of this substance is very difficult, I would recommend again, maybe if you're unsure, to double check. So there are 2 coppers on the left side, 2 coppers on the right side, and also 2 atoms. We possess a total of 4 nitrogen atoms on the left side. Additionally, we also possess 4 nitrogen atoms on the right side. And we have a total of 12 oxygen atoms on the left side. Similarly, on the right side, we also have a total of 12 oxygen atoms. Since this equation is not very simple, in my opinion, such a check could be performed in writing so that you can ultimately visualize it. That is correct. We should proceed to the next example. Barium hydroxide undergoes a reaction with sodium sulfate. So we end up with barium sulfate and sodium hydroxide. Barium hydroxide is an alkaline substance. We have a barium with a charge of 2+, and the OH group has a negative charge. We can work with ion charges. So you see, in certain instances where valence is indicated, it is logical to work with valence. Well, in situations where it is easier, such as when considering oxidation states or ion charges, it is more convenient to approach it in that manner. Sodium sulfate is sodium, and the acidic residue of sulfuric acid. But sodium has a plus charge for SO4, 2 minuses, sodium sulfate. On the right side, we ultimately end up with barium sulfate. We combine barium with the sulfate ion, SO4. Barium has a charge of 2+, while SO4 has a charge of 2. The formula remains valid, it's correct. And sodium hydroxide, sodium OH. Sodium is positive, the OH group is negative. The formula is correct. Now all that's left is to equate. This is called a reaction of exchange or double replacement. Okay, let's begin with barium. There is 1 bar on the left and 1 bar on the right. Now there's only 1 SO4, 1 acidic residue, and 1 on the right too. Next, we will proceed to check sodium. The value of sodium is 2, and on the right side it is 1. Alright, let's check for sodium H2 and OH group. The OH2 group on the left and the OH2 group on the right. Okay, this is the type of reaction that we commonly refer to as a double replacement or exchange reaction. So, how did we do with these examples? I hope it's clear. And we also repeated the reactions, that it is a combination, decomposition, and this is exchange or double substitution, and how we translated a verbal equation into a chemical one. I hope it's clear, and the method of balancing is also clear. Goodbye for today.